Hello and welcome back to this course. In this session, we are going to discuss about ADC. ADC stands for Analog to Digital Converter, and it is the very important part of a microcontroller that is used in most realistic application. So let's understand why we need ADC. Controllers and processors are digital circuits and can handle only the digital data. But signals in the environment like sound wave, temperature, pressure, or any external environment signal are analog in nature. That means they do not give the digital output. If we need to process such type of data, then how we can do this? Here, analog to digital converter comes into picture. ADC is used in most of the realistic applications such as audio processing. It accepts the analog data and convert it into digital data so that we can process it further. Let's discuss some basic ADC terminologies that we'll be going to use in this session. The very first is resolution. I hope you have heard this word resolution. We all watch pictures in TVs, mobiles, or laptop. So in terms of picture, if I talk about resolution, then it is the quality of a picture, that how much pixels can be captured in a single frame. If the number of pixels are large, the picture is clear and the resolution is high. Similarly, in ADC, the maximum number of discrete values that can be used to represent an analog signal is called its resolution. For example, if ADC has 8-bit resolution, then the input signal can be represented using 256 discrete symbols. That means 2 to the power 8. Remember, the resolution of ADC is expressed in number of bits. Next is sampling rate, the rate at which samples of input signal are captured. It is expressed in samples per second. For example, if I say the sampling rate is 10, that means 10 samples will be captured in 1 second. Next is step size. Step size is the minimum value of input signal that can change the digital representation value by next discrete symbol. Let's understand this with a mathematical expression. Let's consider ADC being used at highest resolution of 12-bit. So the maximum number of discrete symbols will be 2 to the power 12. That is 4096. Now reference voltage used for ADC in STM32F4 is 3.3 volt. We need to note that the maximum value will be 4095 as the symbol will start from 0, although there are 4096 symbol if we count from 0 to 4095. So 4096 discrete symbols will correspond to 3.3 volt. Then a single step or a single sample will is equal to 3.3 volt divided by maximum number of discrete symbols, that is 4096. It will gives you 0.00080 volt or 0.8 millivolt. Therefore, the step size will be 0.8 millivolt, which means if 0.8 millivolt is the changed in input signal, then the output value will be changed to next symbol. In simple word, if we have given 0.8 millivolt input to the controller, it will give you in the digital 1. Let's say we have double the value, that means 0.8 into 2, 1.6 millivolt. Then the controller will give you the corresponding digital output which is equivalent to 2, and so on. I hope the idea is clear. Now major blocks of ADC. There are 5 major blocks of ADC, that is input signal, sampling, quantization, encoding, and finally the digital output signal. Let's understand this one by one. Suppose there is an input signal. It's just an example of a voltage signal varying with time. So we have an input signal. Simply we need to convert it into digital data. So the next step will be sampling. In sampling, we will collect various samples of this signal at certain interval of time so that we get a discrete values at different time interval. Once the sample are collected, then samples have been quantized using the quantization technique. That means once the samples are collected, we set a various level for this collected samples, and these quantization values are the maximum number of discrete symbol. So if I am talking about 12-bit, then the quantization value will vary from 0 to 4095. Next process is encoding. That means at each level we have given a code. So let's say the very first level is 1, next level is 2, next is 3, and so on to up to 255 if I am considering this signal conversion at 8-bit resolution. So once all these encoding techniques are done, I have written here decimal output. Basically the encoding is done in digital. That means 1 will be equivalent 0 0 1, next 2 that means 1 0, 3 is 1 1 and so on. And finally we get the digital output signal depending upon the quantization and encoding. I hope you understood the working of ADC, how an ADC works and how input signal, which is analog in nature, is converted into digital. Now let's talk about features of ADC. In STM32F401RE, we have a single ADC with 19 multiplexed channel. That means a single ADC has 19 channels, out of which 16 channels can be externally controlled or used for external sources. 2 channels are for internal sources. One channel is dedicated to VBAT. VBAT is the channel that is used to monitor the battery level. Next is ADC modes. The ADC can be operated in various modes, and those modes are single conversion. That means a single channel can be converted and you can get the digital data. Continuous conversion, that the single conversion or multiple conversion are there, then they can be converted continuously. Discontinuous conversion. Next is scan conversion. That means if we have enabled more than one channel for ADC conversion, then scan conversion, the technique to scan all the enabled channel and convert one by one and gives you the digital data. Next is configurable resolution. As I already said, the resolution is the maximum discrete symbol. So ADC offer you the variable resolution that you can configure. It is from 6-bit, 8-bit, 10-bit, 12-bit. So depending upon the number of bit, the maximum number of discrete symbol vary from 63 to 4095. Next is triggered ADC conversion. If we want to trigger a particular ADC conversion, then we have options for that also. The ADC conversion can be triggered by software as well as hardware. Software triggered means whatever codes we write in our source file, this ADC conversion will take place accordingly. Next is hardware triggered, that is ADC conversion triggered by external source such as interrupt. Next is programmable sampling time. Now each channel can be configured for different sampling time as per the requirement. Suppose we have 4 channels enabled and the input signals on these channels are varying with different rate. Then we can configure the sampling time which is suitable for a particular channel. Next is interrupt generation. ADC offer the generation of interrupt at various stages of conversion, such as conversion complete, watchdog or overrun events. DMA request generation. DMA, that is direct memory access, can be requested during a regular channel conversion for fast data transferability. Now what is DMA? We will be discussing in coming session. And at last, analog watchdog. Analog watchdog is a unit that can detect if an ADC channel is operating within a predefined ADC count window or not. That count window is defined as upper or lower threshold. Like if we have configured a channel for ADC conversion and we want to monitor this converted value within a window of upper and lower threshold. So we can monitor this using analog watchdog. That's all for this session. In the next session, we will see hands-on on ADC.